Welcome back to this channel. So in this video we are going to be handling calculations that are involved in solubility equilibria. So this video is going to be the concluding video of what we call ionic chemistry, or what is also known as ionic equilibria. So this is the finalizing video, and we have given 10 examples that are involved in the calculations of any kind of solubility equilibria. Now, before we proceed, I advise share the video to your friend who has not yet received it, so that you can all benefit as a group. Like we looked at the theory behind solubility equilibria, so in this video we are going to be handling calculations. Now, what you should remember, I told you here in solubility equilibria we can consider mole ratios when you are getting the different concentrations of the different ions present in the saturated solution. So you're going to be calculating equations that are involving solubility and then solubility products. So looking at number 1, we are going to start with the solubility of calcium phosphate to be 0.0011 gram, and this is per 100 grams of water at room temperature. You are prompted to calculate for the solubility product of calcium phosphate, which is present also at room temperature. Now we are going to start by writing the solubility equation of calcium phosphate. And the solubility equation of calcium phosphate, remember I told you you must use double arrows. It's going to give you calcium ions and then phosphate ions. You balance up charges by putting here 2, and then you also put here a 3. Now the expression for calculating solubility product is going to be this. Now, but we need to identify or determine the molar concentrations of calcium ions and the molar concentrations of magnesium phosphate ions. But remember that here we are given mass. So therefore we have to find a way of converting this mass into concentration. But remember that to convert it into concentration we need volume of water in which it was dissolved. So with water they just gave us the mass, that this mass was present in 100 grams of water. So we want to convert these grams of water into volume. Remember that I told you mass is got by density times volume. And if you make volume the subject, you're going to end up with the formula of water, volume of water, to be mass divided by density. So the given mass, it was 100, or its density of water is 1 grams per centimeters cubed. And once you divide the two, you are going to get 100 centimeters cubed of water. So that means that this mass was dissolved in 100 centimeters cubed of water. Now, since we want it in terms of concentration, then what about 1 liter or 1000 centimeters cubed? So 100 centimeters cubed contains 0.0011 grams of calcium phosphate. Then what about 1000? Because we want it in terms of concentration. Now notice that this mass got is going to be grams per liter. But for us to get concentration must be in terms of moles per liter. So we find a way of converting given mass of calcium phosphate, which is present in 1 liter, and we convert it into moles. And that requires us to get molecular mass or relative RFM of calcium phosphate. So since atomic mass for calcium is 40, we get 3 times 40. And that of phosphorus is 31, we get 2 times 31. And that of oxygen is 16, so it's going to be 4 times 16. But the 2 is outside, so it also multiplies that. And you end up with your molar mass to be 310 grams. So to convert the given mass, or the calculated mass that you have got in liter, we have to get the given mass, which is present as this, divided by the RFM. And that is going to be our concentration. So we get 0.011 divided by 310. And the whole thing, if you put it in the calculator and you put your calc in terms of standard deviation, you're going to have 3.548 exponential negative 5 moles. Now if you go to calcium phosphate, that means that, remember that this mass was present in 1 liter. That means that after converting it into moles, we are going to be having concentration, and this concentration is going to be for calcium phosphate. But remember that in the expression of KSP, we don't need molar concentration of calcium phosphate, and I told you that in solubility equilibria is where we use mole ratios to determine the concentrations of the ions. So since the concentration of calcium phosphate is this, what about the concentration of the others according to mole ratios? So you're going to say that since mole ratio of calcium phosphate to calcium ions is 1 to 3, then that means that molar concentration of calcium ions is equal to thrice the molar concentration of calcium phosphate. and you have already got the molar concentration of calcium phosphate to be 3.548. So this is going to be 3 multiplied by 3.548 exponential negative 5. Putting everything in the calculator, you're going to get 1.06 exponential negative 4 moles per liter, or molar, since we are getting in terms of concentration. We also compare the mole ratio between calcium phosphate and phosphate ions. Since it's 1 to 2, that means that the molar concentration of phosphate ions in that solution is going to be twice the concentration of calcium phosphate concentration. Putting everything in the calculator, you're going to end up with 7.096 exponential negative 5 molar, or moles per liter, as the molar concentration of the ions. Now that means that we have qualified for all the requirements required by the KSP formula. KSP say that is equal to molar concentration of calcium ions times molar concentration of phosphate ions. Each must be raised to the appropriate powers, and the appropriate powers must be the coefficients used in balancing of the respective ions, just like we looked at it in chemical equilibrium. So substituting for the concentrations we have calculated, each raised to each power, also here each raised to each power. Now remember that the units are the same, but here the power is going to be 3 plus 2 to be 5. That's why I put here moles per decimeters cubed power 5. That's how we are multiplying these values. So putting everything in the calculator, you're going to end up with your solubility product to be 5.997 exponential negative 21 moles power 5 decimeter power negative 15 as your SI unit. Question 2, you are going to be calculating, provided the solubility product of zinc hydroxide is given as 4.5 exponential negative 17 at room temperature, which is always 25 degrees Celsius. Now we are prompted to write an expression that can show the solubility product of zinc hydroxide. Now first of all, you are supposed to write the equation for the solubility, or showing the solubility equilibria of zinc hydroxide in solution. And then after you write this expression that I gave, I left out the equation, but you're supposed to write it in your books. So case P, after writing the equation, is going to be molar concentration of zinc times molar concentration of the hydroxide raised to power 2 as the appropriate power, or the stoichiometric coefficient. Now in part B, we are going to be determining the concentration in moles per liter of zinc ions and then the hydroxide ions present in the saturated solution of zinc hydroxide at the same temperature. And we are going to do that by first letting the solubility of zinc hydroxide in water to be a specific letter. For example, here we let it to be p moles per decimeters cubed. Now we compare mole ratios. So molar concentration of zinc hydroxide is going to be p mole per decimeters cubed. So we compare mole ratios between the zinc hydroxide and then the zinc ion, and it's going to be 1 to 1. That means that the molar concentration of zinc hydroxide is the same as the molar concentration of zinc ions, which is going to stay p moles per decimeters cubed. We also compare the mole ratio from the equation that you wrote earlier on, that I've told you to write. We also compare the mole ratio between zinc ions and then the hydroxide ions, and you're going to find that the ratio is going to be 1 to 2. Then you're going to find that molar concentration of the hydroxide ions is equal to twice the molar concentration of zinc 2 ions, which is going to be 2p moles per decimeters cubed. Now we bring back the expression that is used to calculate for solubility equilibria, and then we substitute for our molar concentrations. So this is going to be p times 2p but raised to power 2. So this 2 multiplies this, squares this 2, we get 4, and then squares this p, we get p squared. Then p squared times p, you get 4p cubed. And this is going to be your solubility equilibria. Remember that the solubility product was already given in the question as 4.5 exponential negative 17. So proceeding with part C, we are going to state how the solubility of zinc hydroxide would change if its saturated solution is treated with aqueous zinc sulfate. Now remember that we have just covered these ones in the previous video, where we looked at common ion effect and we looked at explanations involving complex ion formation. I hope you understood them and you know what you're going to be talking about here. Now since they use the word of stating, there's no need to explain. You just state what is going to happen to the solubility. Do not explain. If they tell you to explain, you can go ahead and explain. But here, we are just stating. So part C, number 1, if you add zinc sulfate, since we have common ion effect, we say that effect of common ion effect is to increase precipitation and thus decrease solubility. So you're just going to simply say that solubility is going to decrease. And then in part 2, part C, part 2, we shall be saying that here solubility of ammonia solution is going to increase, because for part 2, zinc ions are going to react with ammonia. That means that the solubility equilibria reaction is going to be affected. More of the zinc hydroxide dissolves to replace the zinc ions that are being taken up. So that means that more of the zinc hydroxide, as more of the zinc hydroxide is dissolving, that means that it's increasing its solubility in ammonia solution. So addition of ammonia solution is going to increase solubility of zinc hydroxide. Now here, this was completion of this statement, finding the molar concentrations of the hydroxide and the hydroxide and the zinc ions. So here, provided the solubility equilibria, we make P cube the subject, and this is going to be 4.5 exponential negative 17 divided by 4. Putting everything in the calculator, you're going to end up with 1.125 exponential negative 17. Then to make P the subject, you find cube root on both sides, and you're going to end up with your final answer of P to be 2.24 exponential negative 6. But remember that molar concentration, that means that this P represents molar concentration of zinc hydroxide, and therefore we say that molar concentration of zinc ions, since molar ratio is 1 to 1, is also going to be the same. Now molar concentration of hydroxide ions, since molar ratio is 1 to 2, is going to be twice the molar concentration of zinc hydroxide, or that of zinc ion, which is going to be 2 times 2.24 exponential negative 6. Then you end up with your final answer being 4.48 exponential negative 6 moles per decimeters cubed. Like we said, solubility here is going to increase because of formation of a complex ion when we add ammonia solution. Now looking at part D, where they told us to explain our answer, we are going to say that addition of zinc to sulfate, just like I said, this is common ion effect. You give an explanation for common ion effect, and then Roman number 2 was about complex ion formation. So you need to understand or to properly present them in a correct way, in a correct well-explained way. So here we are going to be saying addition of zinc sulfate solution is going to decrease solubility of zinc hydroxide, and this is because zinc sulfate is containing zinc ions which are common to zinc ions that are present in our sparingly soluble salt of zinc hydroxide. So here we are going to be saying the excess zinc ions added are going to combine with hydroxide ions in solution to restore equilibrium by precipitating the zinc hydroxide, just like I was explaining in the previous video. Here I just want to highlight, in order to restore the equilibrium and also maintaining the value of equilibrium constant. So addition of ammonia, just like I already said, this is complex ion formation, is going to increase solubility of zinc hydroxide. And the reason for that is because ammonia solution is going to react with zinc ions, leading to formation of a complex of tetraamine zinc 2 ions. And you are always supposed to write that equation leading to the formation of that complex because it carries a full mark. So here we are going to say this is going to lower the concentration of zinc ions, and then more zinc hydroxide dissolves to restore the equilibrium and maintain the value of our equilibrium constant, or someone else can say unchanged. So let's look at number 3. Number 3 here is saying magnesium hydroxide is a sparingly soluble salt in water. So number 1, we are going to write the equation for the solubility of magnesium hydroxide in water, which is always the first requirement. After writing the equation, we'll write the expression for determining the solubility product of our magnesium hydroxide. And then after that, if the solubility product of magnesium hydroxide at 18 degrees Celsius is going to be 4.2 exponential negative 12, we are supposed to calculate for the solubility in moles per liter that is present at 18 degrees Celsius of magnesium hydroxide. So try to pause the video and you try out this question, because this calculation is the same as the previous question, which was number 2. So pause the video and test this out as I proceed in 5 seconds. The solubility we are calculating, Roman number 1, it must be present in water, and also we calculate solubility when we have placed our salt in a solution of 0.01 molar sodium hydroxide. Then you are required to comment on the answers that you have got in both Roman number 1 and Roman number 2. So part A, writing the expression for the solubility equation. We write magnesium hydroxide being a solid plus the aqueous condition to get our saturated ions, which is magnesium ions and then the hydroxide ions. Always don't forget that whenever you write a solubility equation, arrows must be reversible. So the case P, or the solubility product equation, is going to be product of the molar concentration of our products. We said we don't include magnesium hydroxide because we assume that its concentration remains the same at the beginning and the end of the experiment. So this is molar concentration of magnesium ions multiplied by the molar concentration of hydroxide ions. But the hydroxide ions is raised to power 2, which is its stoichiometric coefficient. So Roman number 1, let's calculate for the solubility provided magnesium hydroxide dissolved in water. So first of all, we let the solubility of magnesium hydroxide to be X moles per decimeter cubed. Now if the molar concentration of, that means that solubility, remember that I told you solubility is the same as the molar concentration or concentration. So that means that the molar concentration of magnesium hydroxide is going to be equal to X moles per decimeter cubed. Now we use mole ratio to determine the mole concentration of magnesium ions and the hydroxide ions. Therefore, since mole ratio between magnesium hydroxide and magnesium ions is 1:1, that means that molar concentration of magnesium ions is also going to be X moles per decimeter cubed. Now, since mole ratio between magnesium ions and hydroxide ions is 1:2, then that means that molar concentration of hydroxide ions is equal to twice the molar concentration of magnesium ions, and this is going to be 2x moles per decimeter cubed. Now the solubility product, or the equation, the solubility product formula is going to be molar concentration of magnesium ions times molar concentration of hydroxyl ions squared, and then we substitute for the molar concentrations. After substituting for the molar concentrations, make sure that you do not use a square bracket anywhere. So this is going to be X multiplied by 2x raised to power 2. But remember, we are given solubility product in the question, which was given as 4.2 exponential negative 12, which is going to be equal to a net of 4x cubed, just like in the previous explanation. So we make x cubed the subject by getting 4.2 exponential negative 12, dividing it by 4, and then you are going to end up with 1.05 exponential negative 12 if you put everything in the calculator. So making x the subject, we find cube root on both sides, and then you end up with a cube root of 1.05 exponential negative 12. Putting everything in the calculator, you're going to end up with 1.02 exponential negative 4 as your molar concentration or solubility of magnesium hydroxide. Therefore, you are going to make a conclusion that therefore the solubility of magnesium hydroxide in water is going to be 1.02 exponential negative 4 moles per decimeter cubed. Now let's calculate. Now remember that if you look at, we are adding magnesium hydroxide. If you compare sodium hydroxide and magnesium hydroxide, they are both containing a common ion. That means that here we expect solubility to be decreased. And in what? When you add sodium hydroxide. So let's look at that in calculation. So first of all, we have to write the solubility of magnesium hydroxide, which is when it's dissolved in 0.01 molar sodium hydroxide, to be Y moles per decimeter cubed. Remember that sodium hydroxide is a strong electrolyte, or it's a strong base. So sodium hydroxide fully ionizes, forming sodium ions and then hydroxide ions. But remember, the molar concentration of sodium ions is 0.01. Now, since the mole ratio is 1:1:1, that means that each and of every ion is going to have a molar concentration of 0.01. Remember that magnesium, the solubility equation for magnesium hydroxide is going to be magnesium ions plus 2 hydroxide ions. So assuming that the molar, as related, the solubility of magnesium hydroxide in sodium hydroxide to be Y, we compare mole ratio. Since it's 1:1 between magnesium hydroxide and magnesium ions, we also put here Y. And since it's 1:2 between magnesium hydroxide and 2 and hydroxide ions, we put here 2Y. And that means that molar concentration of magnesium ions is going to be equal to Y moles per decimeter cubed. But if you have to compare this equation and this equation due to common ion effect, That means that the molar since we're having here hydroxide and you're also having here hydroxide, that means that the total hydroxide concentration that we are having in solution is going to be 0.01 plus 2y, because it's a common ion effect. So the total molar concentration of hydroxide ions present in that solution, we get the concentration present from sodium hydroxide, and then we also add the concentration present in our saturated ion of the hydroxide. So the new concentration of the hydroxide ion is going to become 2y plus 0.01. But here, remember that magnesium hydroxide is spirally soluble, so we expect it to dissolve in minute quantities. That's why we make an assumption that here, but y is very small, such that 2y plus 0.01 is assumed to remain the same concentration as that of only sodium hydroxide. Now there are two reasons for that. We can first go back to the knowledge of basic buffers. Under basic buffers or buffer solutions, we say that when an ion is already present, it suppresses the ionization of the other elements. Now, provided here, sodium hydroxide is a strong electrolyte, so it fully ionizes, or it's a strong base. So it fully ionizes to give off very many hydroxide ions in solution. So now this is an equilibrium equation. Since it's an equilibrium equation, the magnesium hydroxide has to ionize in such a way, or it has to dissolve in such a way that products must be equal to reactants, the concentration. Now, if hydroxide ions are already present, which are being formed here, that means that it's going to suppress the ionization of magnesium hydroxide to form these ions. And we assume that very small quantities are going to be formed. So 2y is assumed, 2y, the total concentration of the molar hydroxide ions is only assumed to come from the strong base. So always remember that. When you're having a common ion effect, the molar concentration of the common ions, of the ion which is common in both the electrolytes, is assumed to come from the strong base. So we assume that here the total molar concentration is assumed to be only that of a strong base, which is going to be 0.01. That's why we use approximate signs. Therefore, that means that molar concentration of our hydroxide ions is going to become 0.01. But make sure that you have to make this approximation, that y is very small, such that total molar concentration is equal to that from the strong base, which is 0.01 moles per decimeters cubed. So we write the expression for finding KSP and then we substitute for the answers. But remember, molar concentration of magnesium in this case is going to be y, molar concentration of the hydroxide is going to be coming from the strong base, or the strong component that ionizes fully, so which is going to be 0.01 squared. Putting everything in the calculator, this must be equal to the solubility product which was given. Solubility product always remains constant. It's going to be 4.2 exponential negative 12. So making y the subject, you are going to have 4.2 exponential negative 12 divided by square bracket of 0.01. Putting everything in the calculator, you're going to end up with your solubility of magnesium hydroxide to be 4.2 exponential negative 8 moles per decimeters cubed. And therefore, you are going to make a conclusion for the calculation number 2, that therefore solubility of magnesium hydroxide in 0.01 molar sodium hydroxide is going to be 4.2 exponential negative 8 moles per decimeters cubed. Now part C is requiring us to compare this one and this one. Now since this is negative 8 and this is negative 4, we expect this one to be very smaller as compared to this. So our comment is going to be solubility in sodium hydroxide of solubility of magnesium hydroxide in sodium hydroxide is very low as compared to that in water. So let's put that in words. So that magnesium hydroxide is more soluble in water than sodium hydroxide, and the reason for this is the decrease in its solubility in sodium hydroxide is due to common ion effect. So that's how common ion effect can be set in terms of calculations. Now let's look at this. So the solubility of little sulfate in water is going to be 0.035 grams per decimeters cubed. But always remember that concentration must be in terms of moles per decimeters cubed. So these grams must be converted to moles first. That's the first step always. That means that you are required to find molar mass. at 17 degrees Celsius. The temperature is to tell you that temperature is kept constant. Now you are required to calculate for the solubility of lead-2 sulfate when it is present in 0.02 molar lead-2 nitrate solution at the same temperature in terms of grams per liter. So first of all, we write the solubility equation of our lead-2 sulfate, which is sparingly soluble. So lead-2 sulfate in terms of solid, when you add it to an aqueous solution, we get its aqueous ions present in the saturated solution as lead-2 ions and sulfate ions. But whenever you are writing this equation, always remember that we use partial arrows. So the formula for finding solubility product of lead-2 sulfate in solution is going to be molar concentration of lead ions times molar concentration of sulfate ions. So since we are given concentration in terms of grams per decimeter cubed, you have to convert it in terms of moles per decimeter cubed. That means that you have to get molar concentration of lead-2 sulfate. And molar atomic mass of lead is 207, atomic mass of sulfur is 32. Now here we missed some important or vital step, which was supposed to be 4 times 16 to get 64, to show that the 4 atoms of oxygen are present. Adding everything in the calculator, you're going to end up with your molar mass to be 303 grams. So to convert given mass in terms of into moles, we get the given mass divided by the molar mass. And the calculator is going to give you 1.16 exponential negative 4 moles. And therefore, we conclude that the molar concentration of our lead-2 sulfate is going to be 1.16 exponential negative 4 moles. But we go back now, we are not interested in the molar concentration of our sparingly soluble salt. We are interested in the molar concentration of the ions present in its saturated solution. So we use mole ratio, and if you are to look at this equation, mole ratio is 1 to 1 to 1. Therefore, the molar concentration of lead sulfate is the same as the molar concentration of lead ions, and it's the same as the molar concentration of sulfate ions. So we come back and we write the formula of finding solubility product, and then we substitute for everything, and then we square because the respective ions have the same concentration. Now, putting everything in the calculator, you're going to end up with your final answer of the solubility product to be 1.33 exponential negative 8 moles squared per decimeters power negative 6. Now let's calculate for the solubility of lead-2 sulfate when it is present in lead-2 nitrate. Also remember that this is common ion effect because lead-2 sulfate and lead-2 nitrate have lead-2 ion in common. So we are going to let the solubility, our new solubility of lead-2 sulfate present in lead-2 nitrate to be X. Now write the equation for the full ionization of lead-2 nitrate since it's a strong electrolyte. When lead-2 nitrate ionizes, it gives us lead ions and nitrate ions. Always ensure that charges are balanced, so we shall put here 2 to balance charges. And you find that obviously also other atoms are going to be balanced. But remember that the concentration which was given here is 0.02, and by mole ratio, that means that it's going to be the same concentration as the others. Now we also rewrite the solubility equilibria equation, or the solubility equation for lead-2 sulfate, which is our sparingly soluble salt, giving us lead ions and sulfate ions, having our new solubility to be X, and according to mole ratio, since mole ratio is 1 to 1 to 1, also here is going to be X and also here is going to be X. So it means that molar concentration of our lead ions is new molar concentration of our lead ions. Since they are common, new molar concentration is going to be equal to this one up here from lead-2 nitrate plus this one. So new molar concentration of lead-2 ions is going to be summation of 0.02 plus X moles per decimeters cubed. But just like I've explained in the previous video, this is an equilibrium equation. The ions that are being formed here were already formed from the fully ionized lead-2 nitrate, just like I explained in buffer solutions. So the dissolution of this one is going to be very minute. So we expect X to be very small. That's why we make this assumption. But X is very small such that the all of this is equal to only the concentration from the strong electrolyte which is present. So we assume that the all of the molar concentration of lead-2 ions is going to approximate to 0.02. But I've always told you, do not leave out this condition. So that means that our new molar concentration of lead-2 ions is going to be the concentration coming from the strong electrolyte added, which is lead-2 nitrate, which is going to be 0.02 moles per decimeters cubed. The molar concentration of sulfate remains to be X. So since we have already calculated for solubility product, we are just going to substitute it here. in the formula. So we write the formula, and molar concentration of lead is 0.02, molar concentration of sulfate is X. But you have already got our KSP already to be 1.33 exponential negative 8. So we put it here and equate it to our expression. Making X the subject, you're going to have 1.33 exponential negative 8 divided by 0.02. Putting everything in the calculator, you're going to end up with 6.65 exponential negative 7 mole per decimeters cubed. Calculating, therefore, we are going to be concluding that the solubility of, since mole ratio is 1 to 1, remember that I told you molar concentration of sulfate ion is going to be the same as molar concentration of lead to sulfate. So therefore, the solubility of lead to sulfate in 0.02 molar lead to nitrate in terms of grams per liter. Now remember that this is in terms of moles per liter. So we have to convert moles into grams. Remember that I told you RFM or molar mass contains 1 mole. Then what about this moles? That means that 1 mole contains RFM, which is 303, as we calculated it earlier, here, up here. Then what about these moles? So we just get 3.03 multiplied by 6.65 exponential negative 7. Putting everything in the calculator, you're going to end up with 2.01 exponential negative 4 grams per decimeters cubed as your final solubility of lead to sulfate in terms of grams per liter present in lead to nitrate. So let's go to number 5. Now number 5, just like we have been doing, we are going to write the solubility equation for the solubility of silver chromate in water. Then write the expression for the solubility product of silver chromate. Then after that, the solubility of silver chromate at room temperature is going to be 3.207 exponential negative 2 grams per liter. But remember that I told you whenever you're having grams per liter, always your first step is to convert it into moles per liter. So you are supposed to calculate for the solubility product of silver chromate at that temperature. Now in part C, if at all the solution containing silver ions was separately added to a solution containing 5 exponential negative 3 moles of chromate ions, remember that will be common ion effect. And if you remember, the effect of common ion effect is to reduce solubility. And also that one of 5 exponential negative 3 chloride ions. Now for chloride ions, it's not common ion effect, but it will be the other aspect that we explained in the previous video, whereby the concentration of silver ions are going to be reduced, affecting the value of equilibrium. So more of this one will dissolve to produce the taken silver ions. So we expect this one to be increasing solubility of silver chromate. Now we are supposed to state which of the salts, silver chloride or silver chromate, would precipitate first, and we are supposed to give a reason for our answer, provided that solubility product for silver chloride is going to be 1.96 exponential negative 10. Now let's look at that in terms of calculations. So first of all, the solubility equation for silver chromate is going to be the following. So to balance charges, we put here 2. And always when you balance charges, always your equation is going to be balanced, provided you use partial arrows or reversible arrows when you're writing it. So expression for solubility product of silver chromate is going to be this. Silver ions raised to power 2 because the 2 is present here as a coefficient. So since we are given solubility in terms of grams per liter, we are supposed to convert the grams in terms of moles. So we are supposed to calculate for what we call molar mass. So molar mass of silver chromate is going to be 2 times 108 plus 52 plus 4 times 16 to get you 3332 grams. Convert our grams or given solubility in terms of grams to moles, we are supposed to get the grams which are present in 1 liter. We divide them with our molar mass. So our molar mass is going to be 9.66 exponential negative 5 moles. When you put everything in the calculator, that means that the molar concentration or the solubility of silver chromate is going to be 9.66 exponential negative 5 molar. So we compare the mole ratio. Since in the case P, we are interested in the molar concentration of silver ions and chromate ions, we compare mole ratio since we already have the molar concentration of silver ions. So mole ratio between silver chromate and silver ions is 1 to 2. So that means that molar concentration of silver ions is going to be twice the molar concentration of silver chromate ions. And if you do that, you're going to get the answer that you got in the previous slide. Though I didn't explain that, it was above here. So also here, we consider that since mole ratio of silver chromate to chromate ions is 1:1, that means that they have the same concentration. Chromate ions have the same concentration like the silver chromate concentration, which is going to remain as 9.66 exponential -5. Now we find Ksp by substituting for the molar concentrations that we have calculated. I say that to get that one of silver, we have already calculated it in the previous board, which was twice the molar concentration of this. So we substitute for what you have got. So silver ions, we got 1.93 exponential -4, and it's going to be raised to power 2, multiplied by the molar concentration of the chromate ions, which is the same as molar concentration of the silver chromate. Putting everything in the calculator, you're going to end up with your final answer to be 3.60 exponential -12 moles per decimeters cubed, decimeters per -9. Now we are supposed to calculate for the Ksps provided we have added the silver chloride ions. So here we are going to, Ksp always remains constant. I already told you that. So first of all, we make sure that we get the molar concentration of the silver ions present. So provided we put here, or we substitute for our Ksp, which remains constant, and write the equation for finding the expression for finding solubility product of silver chromate, provided that our chromate ions are going to be the concentration they gave us, which is 5.0 exponential -3. So we make concentration of silver ions the subject, and you are going to get it after putting everything in the calculator to be 2.68 exponential -5 mole per decimeters cubed. But for silver chloride, we go Ksp is equal to its ionic product. Ionic product of silver chloride is equal to this. But you are given the solubility product of silver chloride to be 1.96 exponential -10. So we also calculate for the molar concentration of silver ions present. If I told we are given the chloride concentration of 5.0 exponential -3. Now here we are going to be getting our molar concentration of silver ions to be 3.92 exponential -8. Now we compare the two results with addition of chromate ions and then with the one which was added, chloride ions. And you're going to be saying that silver chloride would precipitate first because it requires a lower concentration of silver ions to be formed. If you compare the concentration when you added chloride ions, is lower as compared to this one. This is power -8, which is too low as compared to power -5. So that means that silver chloride is going to precipitate off first because it requires a lower concentration of silver ions to be formed. Now let's proceed with number 6. Number 6, we are going to be looking at calcium hydroxide as our sparingly soluble salt present in water. Now first of all, we are going to write the expression for the solubility product of calcium hydroxide. And in part B, if the solubility product of calcium hydroxide in water at this temperature is 2.8 grams per liter, calculate the molar concentration of the following questions. We're going to be calculating molar concentration of calcium ions and molar concentration of hydroxide ions. In part C, we calculate for the solubility product of calcium hydroxide at the same temperature, and we give its SI units, provided atomic mass of hydrogen is 1, atomic mass of oxygen is 16, and atomic mass of calcium is 40. Now Roman number 2, we are going to calculate for the volume of the 0.5 molar potassium iodate that must be added to 1 liter of a saturated solution of calcium hydroxide above, so as to precipitate calcium iodate at the same temperature, provided the solubility product of calcium iodate is 6.47 exponential -6. So first of all, the expression for Ksp, like I told you, you are first supposed to write the equation. The equation will guide you on writing the correct expression. There I skipped it. So Ksp is equal to this, molar concentration of calcium ions times the square of the molar concentration of hydroxide ions. Now since we are given our solubility in terms of grams per liter, we are supposed to convert it in terms of moles per liter as our first step. That means that we are supposed to calculate for the molar mass of calcium hydroxide, which is going to be 40 since for calcium, and then 2 times 16 for oxygen to get 32, and then 2 times 1 for hydrogen to get 2. Adding up everything, you are going to end up with 74 grams. Now to get moles, we get the given mass which was given in terms of grams per liter, we divide it by 74, which is our molar mass, and we are going to end up with moles of 0.0378, and that's going to be your concentration or solubility. Now write the equation for the solubility of calcium hydroxide in water. Now we are going to consider more equations so that you can get the molar concentration of calcium ions and hydroxide ions, which are required in the equation, or in Roman number 1 and Roman number 2. So we're going to say that molar concentration of calcium ions in Roman number 1 is going to be 0.0378, since the small ratio between calcium hydroxide and calcium is 1:1. And molar concentration of hydroxide ions is going to be twice the molar concentration of calcium ions, since in the equation its small ratio is 1:2. So it is going to be 2 times 0.0378, which was the concentration for calcium hydroxide, or which was the solubility of calcium hydroxide. You should know that concentration is the same as solubility. Putting everything in the calculator, you're going to end up with your molar concentration to be 0.0756 molar. Now in part C, we are going to calculate for the solubility product of calcium hydroxide. So you have to write the expression first of all. After writing the expression, we substitute for the required values. After substituting for the required values, you are going to end up with 2.16 exponential negative 4. And then we also calculate for the SI units. But remember that here, the SI unit for each concentration is moles per decimeters cubed. But since here the powers are going to be 1 plus these 2 here, we are going to be having cubed. So we square moles per decimeter, we cube moles per decimeters cubed. That's why you're having your SI unit to be moles, mole cubed, decimeter power negative 9. After inserting this cubed on this mole and also in the decimeters cubed. You must be very good at calculating SI units in all equilibria, provided chemical equilibria and ionic equilibria. But we are going to first write the solubility equation for calcium iodate, and it's going to be calcium plus iodate ions. We balance charges by putting here 2. So write the solubility expression for calculating solubility product of calcium iodate. Now you are provided with KSP to be 6.47 exponential negative 6. Molar concentration of calcium ions, you already have it above as 0.0378. So we are required to calculate for the molar concentration of iodate ions. So making molar concentration of iodate ions, you're going to end up with the square root of 6.47 exponential negative 6 divided by 0.0378, which is going to end up with 1.31 exponential negative 2 mole per decimeters cubed. But however, from potassium iodate, remember that potassium iodate is a strong electrolyte. So for it fully ionizes to form potassium ions and iodate ions. So that means that comparing mole ratios, since mole ratio is 1:1 between potassium iodate and also the iodate ions, that means that molar concentration of the iodate ions is the same as molar concentration of potassium iodate, which was given as 0.5 molar. So we have to calculate for these moles that are present of iodate ions in terms of the ones that we have got here. So these moles that you are having here for potassium iodate, which are the same as iodate ions, are present in 1,000, since molar represents 1,000. So you're going to say that 0.5 moles of iodate ions are contained in 1,000. Then what about these moles that you have calculated here are contained in which volume? So you're going to say, what about the 1.31 exponential negative 2? They are going to be contained in 1.31 exponential negative 2 times 1,000 divided by 0.5. And you're going to end up with your total volume, which is required to be 26.2 centimeters cubed. Now going to the third last question, we are provided that the solubility product of silver chromate at room temperature is going to be 1.3 exponential negative 12. When a saturated solution of silver chromate was shaken with an aqueous solution of silver nitrate, the solubility chromate reduced by 94.5% of solubility in pure water. Now we are provided, or we are prompted to calculate for the concentration of silver nitrate solution present in terms of grams per liter. That's the case for part A. Now in part B, we are going to be calculating when the silver nitrate is saturated with a solution containing both potassium chromate and then potassium chlorate, a white precipitate is formed rather than a red precipitate. We are going to see how this one comes about. Now for part A, we write the solubility equation for silver chromate, since its pairing is soluble. And then you're going to write the solubility of silver chromate to be Y moles per decimeter cubed. That means that molar concentration, since solubility is the same as molar concentration, we say that molar concentration for silver chromate is going to be Y moles per decimeter cubed. Now we use mole ratios, just like I've been explaining, to determine the molar concentration of the different ions present. So molar concentration of silver ions is going to be 2Y, and molar concentration of chromate ions is going to be the same as that of silver chromate, and it's going to be Y moles per decimeter cubed. So we write our expression for calculating solubility product of silver chromate. Then we substitute, and silver product, the solubility product was given as 1.3 exponential negative 12. So for substituting here, we are going to end up with 4Y cubed, because this square multiplies this 2 and also it multiplies this y. So you end up with 4y squared. 4y squared times y, you end up with 4y cubed. So you make y cubed the subject, and you're going to end up with 1.3 exponential negative 12 divided by 4. Putting everything in the calculator, you're going to end up with 3.25 exponential negative 13. So you make y the subject by finding the cube root on both sides. And you're going to end up with your value of y, which is the same as the solubility of silver chromate, to be 6.875 exponential negative 5 moles per decimeter cubed. Now here, we are going to let the concentration of the silver nitrate that was used to be X molar. Remember that silver nitrate is a strong electrolyte and is aqueous, so it fully ionizes in solution to give us silver ions and nitrate ions. So here, since this one is X molar, we use mole ratios. Since mole ratio is 1 to 1, also this one is going to be X molar, also this one is going to be X molar. So we write the equation for the solubility of silver chromate in solution. Now notice that here we are having common ions of silver. That means that total concentration for silver ions is going to be the concentration is going to be the concentration of these silver ions, which is going to be 2 times the concentration of the silver ions that we got. So it's going to be 2 times 3.78 as we got them, as we got the value of y to be 3.78 exponential negative 6 in the question, then plus this x which is coming from this solution. But remember that I told you that here we only consider the concentration coming from the salt that ionizes fully. So we have to write an assumption that, but 2.08 exponential negative 9 is going to be very small as compared, is going to be very small. Therefore, summation of all this 7.56 exponential negative 6 plus x is going to be this, the molar concentration of silver ions is going to be that one that is coming from the strong electrolyte, which is going to be X moles per decimeter cubed. So that means the molar concentration of chromate ions remains the same as 3.78 exponential negative 6 as given in the question. So we write the equation for our expression of solubility product. And then substituting for the solubility product, like I said, that it remains constant. So we remain back with our 3.78 exponential negative 6 multiplied by x squared, remaining with our solubility product, which was given in the question, because for it remains constant, 1.3 exponential negative 12. So making x the subject, we shall find square root, and you end up with your answer to be 5.86 exponential negative 4 moles per decimeter cubed. And this is going to be the concentration of silver nitrate that was used. So we're going to conclude that concentration of silver nitrate used is going to be 5.86 exponential negative 4 molar. But here, remember that it was required in terms of grams per liter. So you have to convert these moles per decimeter cubed in terms of grams. And I told you that 1 mole is contained in the molar mass. Then what about these moles? So it's going to be these moles times the RFM that we calculate. So molar mass of atomic mass of silver is 108, atomic mass of nitrogen is 14, and the total atomic mass for oxygen, 3 oxygen atoms, is going to be 3 times 16 to get 48. And summing up everything, you're going to end up with 170 grams. Continuation. This is a continuation to show you how the previous solubility of silver chromate was attained. For here, we are going to be saying that the concentration of silver nitrate, proceeding with our calculation, concentration of silver nitrate in grams per liter is going to be 170 multiplied by the moles that you have got so that you can express our concentration in terms of grams per decimeter cubed as required by the question. Now for part B, explaining that you are going to say silver chloride has a lower solubility than the silver chromate. In the solution, the ionic product of silver chloride exceeds its solubility product, and we say that if ionic product exceeds its solubility product, precipitation occurs. So we're going to say that in the solution, the ionic product of silver chloride exceeds its solubility product before the ionic product of silver chromate exceeds its solubility product of silver chromate. And therefore, silver chromate can only be precipitated when sufficient silver nitrate has been added to the solution, so that to precipitate all the silver chloride. And then you have to write those equations. Silver ions reacting with the chloride ions to form silver chloride, and then silver ions reacting with the chromate ions to form silver chromate. So let's look at question 8. Now here you are capable of calculating any equation that is involved in solubility equilibrium. So you are required to attempt all this question on your own to test your understanding. So the solution is going to be laid out in 10 seconds. Pause the video, try out the question as you are going to display them. Going to be the suggested solution for that question, and you must be understanding every concept that has been laid out here because everything has been explained. If you didn't, try to discuss the question with your friends. Otherwise, enough examples, 7 examples were enough for you to understand all what has been written here. So make sure that you follow up and you inquire why you didn't understand, or you discuss it with your fellows. So pause the video and consider your solutions with the following solutions. Make sure that whenever you're calculating, you always lay out the SI units, because for you to carry any mark, SI units must be provided at each and every end of the calculation that you make. So always don't forget SI units. To be doing number 9 together so that you can do number 10. So number 9, part A, solubility of little iodide in 0.2 molar potassium iodide at room temperature is provided to be 8.54 exponential negative 4 grams per decimeter cubed. And I told you the first thing to do is to convert grams per decimeter cubed in terms of moles per decimeter cubed. By getting molar mass and then getting given mass, you divide it with the given you divide it with the calculated molar mass. So write an equation for the solubility equilibrium reaction of little iodide. Now in part B, we are going to calculate for solubility product of little iodide, and then we also calculate for the solubility, which is the same as concentration, of little iodide in water. Now part C, we are going to explain the difference between the answer that you have got in Roman number 1 and also Roman number 2. In part B, Roman number 2, above are the solubility of little iodide, which is present in 0.2 molar potassium iodide. So for part A, we write the solubility equation. And for part B, we first start by converting the given mass in terms of moles per liter by getting the RFM of little iodide. So after getting RFM or molar mass of little iodide, we divide it with the given mass, which was 8.544 exponential negative 4 divided by 461. Ending up with 1.85 exponential negative 6. Now molar concentration of potassium iodide in 0.2 molar of potassium iodide is going to be the one that you have converted, grams per decimeter cubed in terms of moles per decimeter cubed. But remember that potassium iodide is a strong electrolyte, so it fully ionizes in solution to give potassium ions and iodide ions. But here iodide ions in potassium iodide are common to iodide ions in potassium iodide. So we write the solubility equation, and you are going to say that therefore molar concentration. Remember that I told you molar concentration here. First of all, we said that it's going to be the summation of the molar concentration from the strong electrolyte together with the molar concentration that we have got from our solubility equilibrium reaction, which is going to be twice the molar concentration of little iodide, since the mole ratio is 1 to 2. So here we are going to have twice molar concentration of little iodide plus 0.2, 0.2 being the molar concentration that you have got from the strong electrolyte. But you always assume that the molar concentration from the solubility equilibrium reaction is always very small, and we assume that the total concentration of the iodide ions or of the common ions present in the other is always going to come from the strong component, which ionizes fully. So molar concentration of iodide ions is going to be the same as the molar concentration of iodide ions from the strong electrolyte, which is 0.2 molar. So you write the expression for KSP and then you substitute for molar concentration of little ions. Since mole ratio was 1 to 1, they remain with the same molar concentration. Times molar concentration of iodide ions, which is 0.2. Putting everything in the calculator, you're going to end up with the solubility product to be 7.4 exponential negative 8. Looking at Roman number 2, we are going to write the solubility of little iodide in water to be x moles per decimeter cubed. Now, since the mole ratio of little iodide to lead ions is 1 to 1, then the lead ion concentration is going to be x mole per decimeter cubed. And that of iodide to little iodide is 1 to 2. That means that molar concentration of iodide ions is going to be 2x moles per decimeter cubed. We'll write our KSP for the reaction and then we substitute. Remember that solubility product remains constant, which remains the same as that you have calculated previously. So it's going to be 7.4 exponential negative 8 to be equal to 4x cubed. Making 4x cubed the subject, you're going to end up with 7.4 exponential negative 8 divided by 4. Putting everything in the calculator, you're going to end up with 1.85 exponential negative 8. So making x the subject, we put cube root on both sides, and you end up with your x or molar or solubility of little iodide to be 2.645 exponential negative 3. And therefore, we conclude that the solubility of little iodide in water in terms of grams per liter, we just need to make sure that we multiply the mass we have got, or the moles, by the RFM, or the molar mass that we calculated earlier on. So solubility of little iodide in water is going to be 461, which is the molar mass, so that you can convert these moles to grams, times the solubility that you have got, or concentration that you have got. Solubility is the same as concentration. So it's going to be 461 times 2.645 exponential negative 3. And you're going to end up with 1.219 grams per decimeter cubed as your solubility of little iodide in water in terms of grams per liter. Now, commenting or explaining part C, we are going to say that the solubility of little iodide in 0.2 molar potassium iodide is lower than its solubility in water. And the reason for this is additional potassium iodide decreases solubility of little iodide. Because if you see potassium iodide with little iodide, they are containing iodide ions that are in common, which is common ion effect. So we say that the excess iodide ions added are going to combine with the little ions to precipitate little iodide. And in this order, they are decreasing its solubility. But they do that so that they restore equilibrium and they keep the value of equilibrium constant. Now you are required to write down number 10. Pause the video, write down number 10, and test yourself to see whether you can fully maximize this number. So pause the video, write the question, and try it out while the video is paused. And then later, replay it to see the solutions on the next page. These are the solutions to the attempted question. If at all you are honest with yourself and you pause the video, so you should have got the following answers. Just like I said, calculations are the same and all the concepts I've already explained them. So you should be understanding each and everything that has been laid out in the script. So follow up step by step to see where you made a mistake from and to see where you got confused. And let me know which region is unclear to you. So pause the video and take the solution or the corrections. And this is the last part of it. This is the last part of that solution. Now, as you're taking your notes, make sure that you know how to convert grams per liter in terms of moles per liter at the end of this video. Now also, you need to know how to convert moles per liter in terms of grams per liter. The conversion from grams per liter to moles per liter is required when you're starting the question, but the conversion from moles per liter to grams per liter will be required when you're presenting your answers. End of this video, we meet together in the next video under physical chemistry, provided that will be electrochemistry. Currently, you are going to be running in organic chemistry as the next videos to be uploaded. Those are the exams success in your papers.